Greetings, class. Today we're going to recap stoichiometry, which should be a review of sophomore chemistry. This is topic 4.5 in the AP curriculum. Most of this, again, should be a review because we did a lot of stoichiometry in your sophomore chem class. This screen shows an overall flowchart, which I will refer to several times throughout the notes, but it kind of gives you an idea of the whole range of stoichiometry problems that can be presented. This may look like an oh my god slide because there's so much on it, but the main takeaway I think on this slide is if you look on the left-hand side of the screen, no matter what units you start with in your stoichiometry problem, the number one goal, the first goal is to get to moles of A. So you would convert whatever units you're given. If you're given mass of your initial substance in the stoichiometry problem, you would use the molar mass to find moles of A. If you're given particles, you would use Avogadro's number, etc. Again, my little phrase is, my mnemonic is, moles of A, you're on your way. And because once you find moles of A, then you can apply the mole ratio, which remember is the coefficient of the second substance that you're trying to solve for, substance B, over the coefficient of A, which was the given substance. The mole ratio takes those moles of A and magically converts them into the moles of B. Once you have moles of B, there are a number of conversions that you can do to get the final units for B. If you want to find the grams of the second substance, then you would use the molar mass. If you wanted to find volume using density, you would solve for mass and then divide by the density to get volume. So this flowchart kind of gives you just the overview, and we're going to go through an example of pretty much every one of these, hopefully most of them quickly, because like I said, the problems that have mass, particles, volume using STP, and volume using density should be a review of sophomore chemistry. The newer items will be solving with solution chemistry and using the ideal gas law equation to solve for pressure or volume of a gas. So now let's briefly review general stoichiometry, calculating moles, mass, particles, or volume. So you always start with a balanced equation. 2Fe2O3 decomposes to become 4 iron and 3 oxygen gas. And so the way these stoichiometries usually go is you're given an amount. If 50 grams of Fe2O3 decomposes, you can calculate the number of moles of O2, the number of grams of O2, particles of O2, liters of O2 at STP, since it's a gas. Remembering STP is 0 Celsius and 1 atmosphere pressure. Or you can calculate volume, not at STP, using the density of oxygen, which I kind of have you over here on the left. Under these conditions of that problem, it'll be 1.8 grams per liter. So let's look at the first setup, calculating moles. Okay, we are given mass of A. So to get to moles of A, we're going to use the molar mass of Fe2O3. Then we're going to use the magic mole ratio. And using the magic mole ratio, we find that's 3 moles of O2 to every 2 moles of Fe2O3 in the balanced equation. And we would solve and get this many moles of oxygen. Looking at the example below that, I asked for grams of oxygen. Well, it's a very similar setup. It starts the same way. You would find moles of A, use the mole ratio to get to moles of oxygen, but we didn't want moles of oxygen. We wanted grams of oxygen, so we would multiply by the molar mass of oxygen, and the answer there is 15 grams. If you're asked to calculate particles, now, particles is not a very practical thing to solve for because you can't really measure them very easily, but it uses Avogadro's number as the final conversion factor. So the initial setup, if you wanted to calculate particles of oxygen produced, You start out the same way with the 50 grams of Fe2O3. You're going to divide by the molar mass of Fe2O3, and then you're going to use the magic mole ratio, because the magic, it converts the amount of A into the amount of B, and that substance B is the desired substance, the one you want to calculate. And because you want particles, whenever we think of particles, we think of Avogadro's number, and you would multiply by Avogadro to get particles. You also know that you can, and probably have done this before, you can use this molar volume of a gas at STP, which is, again, 0 Celsius, 1 atmosphere. You start out the same way, apply the mole ratio, and the molar volume allows you to go directly from moles of oxygen, in this case, to liters of oxygen, because that's a standard amount, that there are 22.4 liters of any gas in 1 mole of that gas under those conditions of temperature and pressure. And solve that, you get 10.5 liters of oxygen. Finally, you can calculate the volume of anything. It doesn't even have to be a gas. You can calculate the volume of anything if you know its density under the conditions of the chemical reaction. So again, calculating volume using density, you're going to start out the same way, because we're still starting with our 50 grams of Fe2O3. We'll divide by the molar mass to get moles. Use the mole ratio again. In this case, though, we need to get to mass and then divide by the density, because there's a relationship there, right? That if you take the mass and you divide it by the density, you will get the volume of that substance. So multiply by the molar mass, and then divide by the density of oxygen under these conditions. And again, we get the answer, if you do the math, of 8.35 liters of oxygen. Okay, now it's time to review limiting reactant stoichiometry. Recall, you might have a limiting reactant when you're given the amount of more than one reactant, and those amounts that you're given when you do the chemical reaction may or may not be in the correct mole ratio. For example, in this reaction, the 10 gram to 90 gram ratio of mass may or may not be in the 2-to-1 ratio required of hydrogen to oxygen in the balanced equation. And whenever that happens, whenever the amounts of reactant given are not in the exact ratio in the balanced equation, one of those reactants will be limiting and one will be excess. So here's a reaction. If 10 grams of hydrogen reacts with 90 grams of oxygen, how many grams of water will be made? And so you know, I think you recall, that is, from sophomore chemistry, that you always want to use the limiting reactant to calculate the yield of product, because the limiting reactant, of course, is the substance that limits the production of product. Now, there are several strategies, there's numerous strategies actually, to determine which reactant is the limiting reactant. But I'm going to show you the way that, in my understanding from the AP chemistry teachers I've talked to, this is the way that the College Board likes to see the limiting reactant chosen. If you have your own way of doing it, it's reliable and it's logical. Continue to use your way. When I give you, though, with this refresher, I'm going to show you the AP chemistry way. And the way it works is you're going to calculate the moles of each reactant. And almost every one of the strategies for determining limiting reactant starts with this step: calculate the moles of each reactant. Then what you're going to do is choose one of the two reactants with the amounts given, and then calculate the moles of the other reactant that would be needed for that amount of the first reactant. Then you're going to compare that amount of moles of the other reactant to how many moles were given in the balanced equation. I'm going to illustrate this with an example with the same chemical reaction. So first, calculate the number of moles of hydrogen, 4.9603. That's actually too many sig figs, but remember, we can carry more sig figs until we get to the end. Calculate the moles of oxygen, 2.1825 moles. Then what I'm going to do here is I'm going to use hydrogen. to calculate the amount of oxygen that would be needed or necessary to react with this amount of hydrogen, this 4.9603 moles. To do that, I use the mole ratio of oxygen to hydrogen from the balanced equation as if I'm calculating the number of moles of oxygen that would be needed for this chemical reaction. What I find using this is that I would require 2.465 moles of oxygen. But when we compare that amount with the amount we were given, so the given amount of 90 grams of oxygen is 2.8 moles, and that is actually more, right? That is more oxygen than is needed to go with the 4.96 moles of hydrogen. So in this analysis, oxygen is the excess reactant, and there would be, if you could actually calculate the number of moles excess of oxygen by subtracting the 2.465 needed from the 2.8125 given, and so that would be about 0.3 something moles too many. But bottom line here is that hydrogen is the limiting reactant. So remember, the way these go again is that you use that limiting reactant amount to solve the original question, which was how many grams of water would be made. So again, we start with the amount given. We're going to use here the mole ratio of water to hydrogen, though. It's a different mole ratio than above because we're not trying to calculate the amount of oxygen anymore. We're trying to calculate the amount of water. So we're going to use the mole ratio of water to hydrogen from the balanced equation. Again, multiply by the molar mass of water, and you get 89.4 grams of water would be made. So hopefully this way of figuring out the limiting reactant works for you. It's actually kind of elegant in a way, and again, I think one advantage to this method is, as I mentioned earlier, the College Board or I may ask you, if you have an excess reactant, how much in excess is it? And the one way you can do that is figure that out is by calculating the moles given, calculating the moles necessary, and then you subtract the amount given from the amount necessary to get the number of moles excess of the excess reactant. Okay? All right. Fine. Now, the last thing in the video will be to cover solution stoichiometry and then gas law stoichiometry. Okay, solution stoichiometry. The key, as it says on the slide, the key to stoichiometry with solutions is the definition of molarity, which says that molarity times volume is moles. So the molarity of the solution times the volume of the solution gives you the moles of the solute. And if you recall, at the very beginning of this review, we said one of our first goals is to find moles of A. Well, if you're given the molarity of solution A, for example, in this case below, sodium phosphate, you're given the molarity and the volume, you can actually calculate the moles of sodium phosphate pretty easily by multiplying the molarity of the solution times the volume of the solution. So let's solve a few solution stoichiometries using this idea of molarity times volume is moles. So this question asks, what volume of a 0.500 molar calcium chloride solution would be needed to react with 3 liters of a 0.275 molar sodium phosphate solution? Okay, and so in doing the initial stoichiometry setup, we know everything there is to know about sodium phosphate. We know its molarity and volume. We have a 0.5 molar solution of calcium chloride, and what we really want to calculate here is how many liters of this would be needed to react with this much given sodium phosphate so that you'd have the perfect mole ratio, right? So you're calculating the amount or the volume of substance B, the calcium chloride, given this amount of sodium phosphate and given the concentration of the calcium chloride. So you can see the way I started on my stoichiometry setup, I'm going to use the molarity of A times the volume of A to get moles of A. So these first two blocks in the stoichiometry setup is the molarity. So it's 0.275, and usually what I do here is I take the big M, that abbreviation, and write it out moles per liter, because then you can see when we multiply that by the 3 liters, that the liters cancel, and these first 2 blocks, that number will be the moles of A, because moles is the units that are left. Well, once you have moles of A, you're going to use the magic mole ratio, and there's 3 moles of calcium chloride for every 2 moles of sodium phosphate. Now at this point, if you do all the cancellations seen in orange up to this mole ratio, you're left with moles of calcium chloride. And to get molarity, to get volume of calcium chloride, you divide by the molarity. Okay, so moles divided by the molarity will give you volume, right? If molarity times volume is moles, right, then moles divided by molarity will be volume. Okay, so I'm just rearranging the equation. I want to find the volume. I take the moles and divide it by the molarity. And again, when you see I get 2.48 liters of calcium chloride would be required. So it would take 2.48 liters of calcium chloride at a 0.5 molar concentration to react with that given amount of sodium phosphate. Let's now look at a variation where there might be a limiting reactant. So this question, number 2 for the solution stoichiometry, says, how many moles of NaCl would form if 100 milliliters of 0.4 molar sodium phosphate reacts with 100 milliliters of 0.5 molar calcium chloride, right? And so you see you're given the amount of both solutions, and what you need to figure out is that 100 milliliters of 0.4 sodium phosphate and the 100 milliliters of 0.5 molar calcium chloride in the correct proportion? And it turns out it's not. So what we're going to do is we're going to calculate the moles of each substance. So to calculate the moles of sodium phosphate given, molarity times volume, so it's 0.0400 moles, and 0.5 moles per liter of calcium chloride, Cc, times its 0.1 liter volume gives you 0.05 moles. Now, I'm going to use sodium phosphate to calculate the amount of calcium chloride that would be needed to react with that much sodium phosphate, as I did in the water limiting reactant example. And when I do that, I use the mole ratio, calcium chloride to sodium phosphate. I find that I would require 0.0600 moles, but I only have 0.0500 moles of calcium chloride. That means calcium chloride is the limiting reactant. In a way, that makes that amount of sodium phosphate irrelevant to figuring out the amount of sodium chloride, because it's going to be in excess, and the calcium chloride as the limiting reactant will run out, stopping production of sodium chloride. So to do the final solution here, I'm going to take that amount of calcium chloride, so use its molarity times its volume to find the moles of calcium chloride. And then I'm just use the mole ratio, 6 moles of NaCl for every 3 moles of calcium chloride from the balanced equation. And I find that I would make 0.100 moles of sodium chloride given the amounts of calcium chloride and sodium phosphate in this problem. As a variation on this theme, I may go on to ask you, the College Board may go on to ask you, what would be the concentration of NaCl in the final product mixture? Well, to this, you kind of have to think about what we added. We added 100 milliliters of sodium phosphate. We added 100 milliliters of calcium chloride. And so whatever product is made will be in a total of 200 milliliters volume. So you're kind of thinking about the concentration. The molar concentration of sodium chloride will be the number of moles of sodium chloride. In this case, 0.100 moles. And that 0.100 moles will be in 0.200 liters. That's 200 milliliters. And so the concentration of sodium chloride that would be made in this reaction mixture would be 0.500 molar NaCl. And lastly, in a simpler setup, how many grams of the solid product calcium phosphate would form? That would be a precipitate, right? So again, this one we already know the limiting reactant in this situation. It's calcium chloride. So its molarity times its volume gives me its moles. I'm going to use the mole ratio from the balanced equation, 1 mole of calcium phosphate for every 3 moles calcium chloride. And then because I want mass, I'm going to multiply by the molar mass of calcium phosphate. And I get that we would make 5.17 grams as a precipitate, and that would settle out to the bottom of the tube. So you can kind of see, I kind of highlighted here some of the calculations that we did. We did this. In question number 2 in yellow. We calculated the moles of B. We calculated the moles of sodium chloride. We went on and calculated the molarity by dividing by the total volume of solution, and we went ahead and used the moles of A and the mole ratio to find the mass of the calcium phosphate product. Last but not least, gas stoichiometry. The key to stoichiometry with gases under different conditions of pressure and volume is the ideal gas law. If you recall, our first step is always calculate or find the moles of A, because moles of A, you're on your way to using the magic mole ratio to figure out the amount of your second substance, correct? So when you think about finding moles of A, we recall that moles is pressure times volume over RT. And if you know you're going to be given the pressure of the first gas, the volume of the first gas, and the temperature of the first gas. That's going to have to be given. We always know the value of R. You will be able to calculate the number of moles of the gas that might be participating in the chemical reaction. And then you can go on and find the amount of product. Let's look at an example or two. Okay, we're back to the equation where we had hydrogen gas and oxygen gas reacting to make water vapor. So how many grams of water would be made if 20 liters of hydrogen gas reacted at 300 K and 2 atmospheres? And so what do we need to do? We need to get to moles of A. So in this case, the moles of A will be the pressure of the hydrogen times the volume of the hydrogen over the temperature of the hydrogen and divided by R again then. So you see what I set up here. These first 4 blocks in my stoichiometry setup are all to calculate moles of A. There's the pressure times the volume divided by R, written in terms of atmospheres because the pressure was given in 2 atmospheres, and divide that by the temperature of the hydrogen. All that gets you moles of A, so now I'm on my way. I can use the magic mole ratio, water vapor to hydrogen. And then since I want to know the grams of water, I will use the molar mass of water. And I can see that I would make 29.3 grams of water. So here, the only variation here so far is in the way that you calculate the moles of your given substance, your starting substance. In this case, it's PV over RT. So in example 1, we were calculating the mass of water vapor, but sometimes the thing that you're trying to calculate is also a gas. And so it turns out you can use the ideal gas equation on the other end, on the B end, on the what you want to calculate end of the stoichiometry. To usually what you're calculating is the volume or the pressure of the second gas. So let's look at the setup for example number 2. You have 2 liters of oxygen reacts with hydrogen. That's going to be in excess because the amount of hydrogen is not given. It's at 400 K and 1 atmosphere. And then when this reacts, the temperature is going to change and the pressure might change in the container. And so what the question says then is what volume of water would be made if the conditions after the reaction are 450 K and 2 atmospheres. So this is going to start where, like it did in example number 1, I need to calculate the moles of oxygen. So I'm going to take my 1 atmosphere times the 2 liters, divide it by R, and divide it by the T. Those first 4 stoichiometry blocks gives me the moles of oxygen. Then I'm going to use the magic mole ratio, 2 moles of water for every 1 mole of oxygen in this balanced equation. So at this point right here, I have the moles of water vapor, okay? But I want to know the volume of the water vapor. And so I'm going to use the ideal gas equation and solve it for the volume of my water vapor. The volume is going to be the moles of that water vapor, which we know right now because these first 5 blocks will get me the moles of water vapor, the little red star there, okay? And then volume is the moles times R times the temperature of that gas over its pressure. So what I do on the outgoing end here to calculate volume of B, it takes these 3 blocks to calculate the volume of B because I need to take the number of moles here, multiply it by R, multiply it by T, and then divide it by the pressure. And if I do all that, I find that the volume of water vapor would be 2.25 liters. Also, notice when you're doing the math here that given the way this is set up, that R appears in the denominator here, it appears in the numerator there. So those would actually kind of cancel out if you're going to do all the math at one time. And that often happens, but I like to include it. And the reason I always include the R and the R on the incoming and the outgoing side is that it allows me to cancel my units and make sure that I've set everything up correctly. So finally, to wrap this up, in that example, we calculated the volume of water vapor. But you can also, if you look over here in the little flow chart on the lower right-hand side, you can also use this setup to calculate the pressure of the gas that you want to know the amount of, gas B, under those final conditions. Because, again, you're still going to have the moles of B, like we did above, after the mole ratio. So instead of calculating the volume as we did down here, what you would do is you would take those moles, multiply them by RT, and you'll be given the volume, and so you would just divide that by the volume, and that would give you the pressure. So again, you can use the ideal gas equation to calculate either pressure or volume of a gas under certain final conditions, given basically any one of these starting amounts of substance A, but in this case we were talking about gas laws, so we used, we had pressure and volume and temperature of oxygen. All right, that wraps it up for stoichiometry in less than 30 minutes. That wasn't too bad. All right, signing off.